Hi, we are Team 5. My name is Doyle, and my lovely teammates are Byungmo and Sejun. Our project is Korean full-board billiard, which we call 사구 in Korean. It's a clean and continuous deterministic sparse reward benchmark, so we built it in Gymnasium and tried to solve this special domain with reinforcement learning. So let me show the game first. So we hit the white ball, and it hits both red balls in one shot to score. The yellow ball is foul. So the white ball curves off the first red into the second one. That's 1 point. The agent sees a physics simulator we wrote wrapped as a gymnasium environment. Each ball has 7 features, so 4 ball makes 28 numbers in total. The action is just 4 numbers: direction, power, and where to hit on the cue ball. One shot simulates in 5 milliseconds. The reward is 1 for touching both red and 0 otherwise. A foul is touching the yellow ball. We tested in 2 ways: a short version, 100 games, and a long version, that runs until the first miss. A random shot almost never scores for 3 reasons. The action is continuous, the physics is deterministic, so there's no luck to save you, and the reward is sparse. First, can playing RL just learn to score? TD3 and SHC are off-policy algorithms, so they replay past shots. PPO is on-policy, so it throws them away. Only off-policy can reuse the rare scores, which happen about 4 times in 100. So off-policy beats PPO about 2.5 times. SAC is our stable pick. So 2 choices here: where it starts and what happened after a miss. Random start and keep playing after a miss wins because it gives the agent the most variety. It had the best average and it was the most consistent. But it flattened out by 250,000 steps, still under 1 point per game. It isn't a compute problem, it's just lack of structure. So, can we help it without new structure? We tried 2 leverages. The first is a curriculum learning. Aims only first, and then power, and then the full action for searching in the action space at each stage. The second one is a learned reward model used as a dense scoring hint, but always tested on the real score. So the result was neither one breaks the ceiling. The best is only 0.8 of a point. The curriculum actually hurt, and the reward model was costly and pointless next to 5 millisecond simulator. Those were useful failures, and the lesson is clear: we need real structure. So let's just hand it the geometry. Here's the table and balls. We force the aim inside a cone that's sure to hit the red, so it only picks where to aim, not whether to hit. All of its effort goes into the good shots. A half of a point jumps into a 2.5 point, which is more than 5 times better. And then same idea on the inputs. We add the current distance and the angle. So that's just 4 extra features and no new physics. So half a point, and then 2.5, and then 6.5 points per game. Per shot, that goes from 1 score in 20 to 2 in 3, giving it the geometry beats any reward tricks. This is the single biggest jump in a war product. So watch it score 9 times in a row with each shot previewed first. Each shot is previewed, so you can read the aim, the power, and the spin before it fires. Reward shaping. Could a richer reward push it even further? A foul penalty and a gentle shot bonus and a near miss bonus. And only the foul penalty helps, and it just makes the agent foul less. The other 2 barely changes the score, so changing the reward doesn't beat real structure. So now we're gonna use inference time search. Now we use the 5 millisecond simulator. Let it verify the shots for us. So we're gonna propose a shot, simulate every one, and then keep the best. And look 1 shot ahead, then play the best one. So there's no learned model here, the simulator itself is just the judge. The longest run we got was 9,392 score in a row against a test of just 10 shots. So we can visualize again, 80 in a row and each previewed. It just doesn't stop. So every single shot here was checked by the simulator before it was played, and that's the word trick. It honestly doesn't stop. We cut it off at 80 just to fit in on a slide. The bitter lesson. It was solved by a clever reward. What's killed was compute through a faithful model. Learning gives a prior, domain knowledge makes it good, and the simulator extended past any limit. Thanks so much for your attention, and we were Team 5.